Greetings, my name is Barry Setterfield. Welcome to this session on the Bible and time. In the previous 3 sessions we've looked at some fascinating stuff, and what we want to do in this session is to bring it all together and show where it leads. In the first session we looked at plasma. You find that plasma is pervasive right throughout space. You have plasma filaments, you have plasma sheets. This makes up the majority of matter, 99% of all matter out in the universe. And plasma is affected by electric and magnetic fields. It is basically following electromagnetism. So plasma and electromagnetism were the first things that we discussed, and we showed how electromagnetism was exponentially stronger than gravity. In the second session we discussed the zero-point energy, something which goes through everything in the vacuum, right throughout space, right throughout everything. It goes through our bodies, our houses, our desks, our computers. It is pervasive, it goes right through everything that we have in the universe. And then in the third session we looked at the speed of light and other atomic constants and how these are affected by the zero-point energy. In this session, despite the fact that these things were interesting in themselves, we want to bring all these together and show what happens when you bring them together and show that there's something which this leads to, which is absolutely amazing. In the Bible, God says 12 times that he stretched out the heavens, or space if you like. It took science a few thousand years after that to discover that space had been rapidly expanded at the beginning. Standard science has no explanation for the energy behind what has been referred to as the Big Bang. But if God did it, then it was his energy that was invested into the fabric of space. You invest your energy into the fabric of a balloon when you blow it up. If you do not tie the balloon but let it go, the potential energy you put into the balloon becomes kinetic energy, or energy of movement. When you release the balloon, it goes flying around the room. This is the energy you put into the balloon being released. What happens to the balloon is perfectly shown by the action of a balloon rocket. When it is let go, the transfer of potential energy to kinetic energy is very rapid at first, but then, as the transfer completes, it slows down and finally stops. This is the same speed curve that we see happened in the universe as the potential energy from the expansion became the kinetic energy of the zero-point energy. The potential energy that God invested into the vacuum of space was vast. The kinetic energy which resulted from this still exists in space everywhere as something called the zero-point energy, or ZPE. It got that name because it is present even in vacuums that have been cooled down to absolute zero. How can we know all this? Let's go back to the redshift in outer space. If you recall, the farther away objects are, the more the light signatures from their elements appear redshifted when compared to our Earth standard. In other words, the elemental signature lines are shifted down towards the red or low energy end of the rainbow spectrum. The standard explanation of this red shift is that it is a sign that the universe is expanding. But astronomers have shown that when you get out past our local group of galaxies, the redshift measurements do not show smooth transitions as they go further out. They rather go out in a series of systematic jumps with distance. This graph shows some results of a study by Guthrie and Napier of 399 galaxies in the Virgo cluster. Distance, and hence redshift, increases to the right on the graph. The preferred redshifts of galaxies are shown by the peaks in the graph. The dotted vertical lines through the peaks show the systematic jumps in redshift at intervals of 71.1 kilometers per second. If the standard explanation that the redshift is a sign of the universe expanding were true, then that would mean that the universe must be expanding in a series of jumps. So, as we discussed in a previous session, the redshift must be due to another cause. We know that matter resists change until the energy exerted on it forces it to change. You see this when you try to push a piece of furniture across the room. It resists at first until you push hard enough to force it to move. Atoms behave the same way. Their electrons circle their nuclei in set patterns with set energy levels. As discussed in detail in our previous presentations, Hayes and Puthoff and their colleagues have shown that the zero-point energy maintains the energy of all atomic orbits throughout the universe. As the ZPE built up, the energy available to atomic orbits also built up. But the orbiting electrons will resist any change until the energy exerted by the ZPE forces an increase in orbit energy. Because the zero-point energy is uniform throughout the cosmos, its increase forced a series of changes of orbit energy simultaneously on every atom in the universe. This means that as time went by and the ZPE was building up, the light signatures of each atom became more energetic or bluer. Blue light is much more energetic light than red light. Its waves are shorter, and so more will pass a given point in a second than red light waves will. When we look out into space, we're looking back in time. The farther out we look, the longer back in time we are seeing. This means that as time went on, light from atoms was progressively blue shifted as it got closer to us in space and time. So when we look far out into deep space and see that redshift measurements are quite high, we can either assume, as standard science does, that the universe appears to be expanding more and more rapidly, or we can assume that the change from potential to kinetic energy at the beginning was going on extraordinarily quickly. The second explanation is the one we prefer here. If that explanation is valid, then we can track the behaviour of the ZPE by looking at the redshift measurements to see how fast the transfer of potential to kinetic energy was happening through time. The mathematical curves will be the inverse of each other, since the redshift drops as the ZPE increases. If the ZPE was changing for all that time, was it affecting anything else besides the shifting of light signatures across the colour spectrum? The zero-point energy is comprised of electromagnetic waves of all lengths, but the vast majority of them are on the shorter end of the spectrum. ZPE waves are going in all directions at once, so they often crash into each other. As we explained on one of the videos before, this means that at the point of crashing, they create a tiny pair of something called virtual particles, a positive and negative pair. Because one of each pair is positive and the other negative, they slam back together very quickly. Today, the all-pervasive zero-point energy is so strong that at any instant the vacuum has about 10 to the 58, that's 1 followed by 58 zeros, 10 to the 58 virtual particles per cubic inch. The important thing to note, though, is that it wasn't always this way. While they exist, virtual particles are capable of acting like solid bits and pieces and can absorb a travelling photon of light. However, the moment they slam back together, that photon of light is re-emitted and goes on its way, until it hits another virtual particle. So the progress of a photon of light through the vacuum is rather like a runner going over hurdles. The more hurdles to jump, the longer the runner takes to complete the course. Likewise, the more virtual particles in its path, the longer the photon takes to arrive. In the beginning, when the ZPE strength was low and just starting to build, there were almost no virtual particles. This meant that light photons were not delayed in reaching their final point of absorption. Today, it takes light over 25,000 years to reach us from the centre of our Milky Way galaxy. In the beginning, with few or no virtual particles to interrupt its journey, that light would only have taken a few minutes. Today it takes even longer, 8 minutes, for us to get light just from our own sun. So what we refer to as the speed of light was affected by the changes in the zero-point energy. As the ZPE built up, the speed of light slowed down. This then gives us an answer to the question that is often asked by creationists and others: how did light get from the distant stars to reach us
if the universe is so very young? The build-up of the ZPE over time offers an answer to that question. The original speed of light was so high that this was possible. This also helps us answer a question which has puzzled cosmologists for decades. We can see that radiation is evenly dispersed throughout the entire cosmos. So how did that happen so quickly? Keeping in mind that light is radiation, we can start to understand that, without interfering virtual particles, all radiation, light included, could travel and thus be spread very quickly. Understanding this, it might then be wondered if the zero-point energy has affected anything else as it has built up over time. All radiation is electromagnetic in character. This includes the zero-point energy. Because of that, it can be shown that all electromagnetic processes are affected by ZPE strength. Since atomic behaviour is governed by electricity and magnetism, then it might be expected that atomic processes, or how atoms behave, would also be affected. Remember that we mentioned that the vast majority of the ZPE waves were on the short end of the spectrum. Many are so short they jiggle electrons, the tiny negative electric charges that circle the inner nucleus. That jiggling actually imparts mass to the electron. Electronic or subatomic mass is not the same mass as we think of it in the ordinary sense of the word. The way we measure the mass of an electron is not to put it on a scale. That would be impossible. So since the electron has a negative charge, we can deflect its path with a fixed magnetic field. The more mass an electron has, the more it resists the magnetic deflection. So the less mass, the more it is deflected. We've been able to measure the small changes in electron mass this way even in our own time. This diagram shows the way an ion or positive charge is deflected. It works exactly the same way for an electron. It follows then that as the ZPE built, so did the jiggle, and therefore so did the mass of electrons and all other subatomic particles. This means they slowed down. The time it takes for an electron to go around in its orbital is one of the ways that scientists today measure something called atomic time. In the past, a lower mass for the electron also meant the electron would travel around in its orbital more quickly. A 2013 photo of a hydrogen atom with an electron going around in its orbital is shown here. The fuzziness is due to the ZPE jiggling. Thus, as the ZPE built up and atomic masses built up, atomic time or atomic clocks slowed down. This is still going on today, but to a lesser extent. Here's an example. This is a graph of Mercury's position at various times in relation to other astronomical objects, such as the Sun and our Earth. The measurements were taken both in terms of atomic time and our orbital time, the time it takes us to orbit the Sun. On the chart, atomic time is plotted vertically, and orbital or gravitational time is plotted horizontally in years. It is clear that even today, the two clocks, or rates of telling time, are not the same. Which leads us to an even more interesting result of a building zero-point energy. We know that very large atoms, such as uranium, are so large that they literally pop off their pieces bit by bit and become, as a result, a more stable element. In the case of uranium, it initially decays to thorium, and then, given enough time, the thorium decays further to become lead. In this example with uranium and thorium, uranium is called the mother element and thorium the daughter element. The rate at which half of a heavy element becomes its daughter element is called its half-life. Then, after one half-life, half of what is left of the mother element will take the same amount of time to decay as the original lump. And then the next half of the half will take the same time to decay, and so on. What we have measured today indicates that each half takes as long to decay as its larger half took. As shown in this slide, it is the proportion of the mother element to the daughter element which is used to measure the age of a rock atomically. In this example, it is the ratio of uranium atoms, the red dots, to the end product of lead atoms, the blue dots, that allows the atomic age to be determined. Today, the rate at which half of the uranium in a rock becomes lead is figured to be about 4.5 billion years. As soon as a rock or crystal is formed with uranium trapped in it, the uranium starts to decay to lead. Scientists look to the ratio between the uranium and the lead to see how old the rock is atomically. So, when they see a rock or a crystal in that rock containing half uranium and half of its daughter element, lead, they say that that rock or crystal is 4.5 billion years old. In contrast to uranium, some elements have very short half-lives. Francium, for instance, decays very quickly. It has a half-life of 22 minutes. Because the number of protons in the nucleus of an atom determine the kind of element the atom is, what happens to the protons in an atom during nuclear decay is the important thing. When a heavy element decays, it gives off three kinds of radiation. Alpha decay is when it loses a small bundle of 2 neutrons and 2 protons together from its nucleus. This bundle is called an alpha particle, but that combination actually is a helium nucleus which has been popped off. Alpha particles are massive enough that a piece of paper can stop them by absorbing them. If an electron pops off, that is beta decay. Electrons are much smaller and no piece of paper can stop them. You need a metal foil to stop beta particles. The most dangerous radiation, however, is not alpha or beta, but gamma radiation. That is pure energy which is released during the decay process. That is the radiation which needs thick concrete and or lead to protect us from it. It might be asked what effect a lower zero-point energy in the past would have on the rate of radio decay. In every element, the protons and neutrons in the nucleus are jiggling around. The heavier the element, the more protons and neutrons there are in the nucleus, and so the more they are hitting each other. Initially, because all the particles have less mass due to the lower zero-point energy jiggling, their velocity is higher. With every hit near the side of the nucleus of a heavy atom, there is a chance that the particle will pop out or escape. So the more often the particle hits, the greater the chance of escape. This means that when the ZPE strength was low, particle velocities were higher, and that meant more hits in a given time near the side of the nucleus, which led to a faster escape rate. When the ZPE is high, particles have more mass and so a lower velocity. This means it is harder for particles or particle groups to escape. Thus, when the ZPE was lower, we would expect that radio decay was faster, and the further back in time we go, the more rapid radioactive decay should be. It has already been shown that there's a discrepancy today between the way atomic time is measured versus orbital time, or the time it takes the Earth to go around the Sun. But when scientists measure atomic ages, they usually assume that the decay rate or rate of movement of atomic particles has always been the same. This would be true if the zero-point energy had always been constant, but the ZPE has increased with time. As the ZPE increased, atomic masses increased due to the increased jiggling caused by the ZPE. This means atomic time slowed compared to orbital time. Orbital time is gravitational, and gravity has remained the same as it's unaffected by ZPE changes. Therefore, orbital time ticks at a constant rate. Before we look into this a bit more, we need to respond to a criticism regarding an increased rate of radio decay. The criticism is that faster radio decay would fry to a crisp anything living at the time. This is not true for two reasons. First, as the ZPE increased, the mass of subatomic particles also increased. That means this radiation could do more damage now than it ever did originally. It would be similar to the difference between being hit by a child racing on a tricycle or a slower moving semi. Which would you prefer? The second reason no life form would be fried by a higher rate of radio decay in earlier times is that the actual intensity of the electromagnetic waves was different. The intensity of a wave of any sort is determined by its height or amplitude. This works on the ocean and in subatomic and electromagnetic processes. On the ocean, high waves are more dangerous than low ones. With light and gamma rays, or electromagnetic radiation generally, this intensity translates into brightness. The image shown here is an example of this. The top waves have very low amplitude or height and are thus actually weak or of lower intensity. The higher the waves, which means the greater the amplitude, the stronger or more intense they get. A low ZPE strength, that is, a low ZPE intensity, also means that all electromagnetic waves had a low intensity or low amplitude. As a result, each gamma ray was less damaging. Higher decay rates in the past certainly meant more waves. The critics are right about this. But each of those waves were of lower amplitude, and when all those extra waves of lower amplitude were added up, the overall intensity would be the same as we have now. Standard astronomy says we live in a universe that is somewhere around 14 billion years old. They are dating it because they assume the rate of atomic processes have been constant through time. In contrast, the Bible indicates we live in a universe that is less than 10,000 years old. If atomic time is correct, and atomic processes have always been the same, then standard astronomy is right. However, if atomic processes have not always been the same, then, whether or not the Bible is correct, some adjustments will have to be made. How would we know how to make these adjustments? For that, we have to go back to the redshift. If the redshift were an indicator of the expansion of space, then space at its farthest limits would be expanding at something like the speed of light. Meissner, Thorne and Wheeler point out in their text on gravitation that this would massively disrupt galaxies out there, tearing them apart. The left-hand galaxy here is disrupting, but this one is not that far away. The vast majority of galaxies we see, as far away as we can find them, look quite stable, like the Pinwheel galaxy on the right. So, as we pointed out in our previous video, the idea that the redshift is caused by movement when we look far out does not work. As we also pointed out, other options for redshift also do not agree with what we actually see. For this reason, we keep coming back to an increasing ZPE as the explanation for the redshift that matches the data best. The only possibility that is left is that the redshift is due to a lower zero-point energy in the earlier stages of the universe. We need to repeat this part right now, for when the zero-point energy was quite low, the light released from electron movement was much less energetic. Compared to what we see today, that means that light was extremely redshifted. As the ZPE built up quite rapidly initially, we see the changes in the redshift far out there also happening very rapidly. The closer we get to Earth, the closer we also get in time. Through time, the ZPE slowed in its increase, and thus the redshifting also became less and less. As the graphs here show, the two curves are the exact inverses of each other. So we have the general form of the ZPE build-up, but we need to know exactly how much it increased since the origin. It is actually possible to discover how much the ZPE has changed since the beginning. The present frequency of jiggling of electrons by the ZPE is called the Compton frequency. This frequency is 1.2355 by 10 to the 20th hits per second. 10 to the 20th is 1 followed by 20 zeros. The actual ZPE strength is related to the square root of this jiggling frequency. Assuming the initial jiggle was minimal, then this frequency reveals that the ZPE strength has increased by a factor of 3.84 billion with a B since the very beginning. It is this figure that tells us how much faster electromagnetic processes were operating initially. We have shown that the increase in the zero-point energy slowed the speed of light as the numbers of virtual particles increased. We have shown how the increased zero-point energy slowed atomic processes. The zero-point energy is also responsible for the electric and magnetic properties of space. Because 99% of everything we see in space is in the form of plasma, and plasmas are electromagnetic in character, that means the ZPE is also responsible for the rate at which plasma interactions and reactions occur throughout the universe. Today, plasma interactions are already much faster and stronger than gravity. A lower ZPE strength originally would enhance that significantly, thereby indicating an even faster time for cosmic processes involving plasma. Up to this point, we have shown there is good reason to suspect the universe as a whole might not be nearly as old as we are told. But if that is true, we have to account for things like the formation of elements, galaxies and stars. In the standard gravitation model, a great deal of time is required for all these things to be made. But the observational data do not permit this length of time. If there is no alternative to that model, there is indeed a time problem. Most models state that the universe started as a rapidly expanding superheated plasma. Standard astronomy says that gravity took over quickly and controlled most of the processes from then on, including element, star and galaxy formation. The first problem with this involves what we see. What we see in space is 99% plasma, in sheets and filaments. Plasma behaves electromagnetically, so maybe that is the direction we should be looking in. Let's look at element formation. The gravitational model states that the Big Bang produced only hydrogen, helium, and a bit of lithium initially. The first attempt to explain all the other elements was to try to work with just those elements in a hot plasma. Big Bang scientists like George Gamow and Nobelist Eugene Wigner pointed out that if hydrogen plus one other element heavier than lithium was present, all the elements would form by fusion processes. Carbon was the element of choice, but an extensive analysis proved that that element did not work. By 1960, they had given up. So a second option was put forward. This option stated that since gravity forms stars, all the other elements were made by nuclear processes in these stars' interiors. When those stars aged and finally exploded, as shown here, the newly formed elements were scattered throughout nearby space. A number of generations of exploding stars were needed to give the abundance of elements we see throughout our galaxy and others. It's estimated this process took about 9 billion years. But these elements are found in the earliest galaxies, so the problem continues. However, around 2010, Edward Bodrow, Professor of Chemistry at University of New Orleans, re-examined the situation involving the first option, the need for another element. He proposed that the element oxygen, instead of carbon, was present with hydrogen in the extremely hot plasma of the early universe. When looked at in detail, Plasma fusion processes show that all other elements in their known abundances can form from this particular mix in a few hours at most. Professor Gamoff's initial calculations on similar processes agreed. He said all the elements could be formed by this way, quote, in less time than it takes to cook roast duck and potatoes. Amazingly, the Hebrew word in the Bible for heavens is shemayim. The word for water is mayim. In other words, the very word for heavens incorporates the word for water in Hebrew. If the originally created plasma was one oxygen nucleus for every 2 hydrogen nuclei, then we have the mix we need for all the other elements to form extremely rapidly by plasma fusion processes. The Bible had the answer to this cosmic puzzle all along. That takes care of elements, and it's in direct agreement with observations of the early universe and the Bible. But what about galaxy formation? There are several gravitational models, and they can be very complex. But somehow they have to account for the fact that galaxies are spinning like somewhat flat plates with bulges in the middle. Getting both the spin and the spiral arm formation to work has taken some ingenuity. One problem they did not expect is the startling discovery that the outer spiral arms are spinning just as fast as the interior arms. Gravitationally, that's impossible. Thus, they've assumed that there must be a massive amount of dark matter out there, providing the gravitational pull necessary. It should be noted that science has not found this dark matter despite an extensive search. However, when we consider the actions of interacting plasma filaments in our labs, miniature galaxies form in 1 or 2/10 of a second, with perfect spiral arms as shown in the sequence here. And those spiral arms spin as fast as the outside as they do on the inside, so no dark matter is needed. Experiments with up to 12 interacting filaments have been done, and all known types of galaxy have been produced. If you've not seen this, it is on one of our earlier YouTube videos. Plasma physics therefore answers the problem of galaxy formation. But what about the time it would take plasma to form galaxies? Gravitationally, a full galaxy is expected to take up to 1 billion years to form. However, when the lab experiments with plasma are upscaled to the sizes of galaxies in the universe, the formation time under today's conditions is about 30 to 40 million years. This is quite a reduction from 1 billion years gravitationally, but another factor is involved which brings a surprise, as we'll see in a moment. Before that, let's look at star formation. In the standard model, matter has to attract itself gravitationally inside a gas and dust cloud. The cloud then contracts gradually, and the particles eventually come together to form a star. But if the matter is moving or becoming compressed, which it must do, heat is given off. As this cloud collapses, the heating would increase. The heat would then drive the cloud apart. This makes gravitational star formation very difficult to almost impossible. Scientists try to avoid this problem by proposing that carbon monoxide molecules would radiate the heat in the infrared and so not affect the cloud. First, they are not yet sure that this would work because the process is still being debated. Secondly, they have already realised that, on their model, carbon is not one of the earliest elements. Consequently, forming the first stars is a problem. Even so, star formation by this process is expected to take from 10 to 50 million years. Let's look at plasma filaments again. Lightning is a plasma filament. We can see how it forks and twists in response to almost any disturbance in the air at all. Because lightning exists simply to equalize charge differentials, it comes and goes quite quickly. But lightning rods are often pinched in the process. Out in space, plasma filaments are very long-lasting. The work in plasma labs indicates a different star formation mechanism. Plasma filaments in space also react to changes in their environment, whether it be varying current flow or temperature change, and all these can cause those filaments to pinch in. These are called Bennett pinches. This pinch forms a plasma ball which goes into arc mode and lights up. And that is exactly what we see in space. Stars, plasma balls, have formed at pinches in their filaments. The lab diagram is on the left, and the others are examples of pinches in filaments forming stars out in space. This is why we see stars lined up like beads on a string in our galaxy and its spiral arms. We can see that happening in Orion on the left image, or along the filaments making up the spiral arms like those in the galaxy M81 on the right. In gravitational astronomy, star formation is expected to take from 10 to 50 million years. When plasma experiments done in the physics lab are upscaled to universal proportions, star formation would take about 17,000 to 18,000 years. But there is one more factor involved which brings surprising accord with the Bible, namely the zero-point energy. As pointed out earlier, the zero-point energy strength is the inhibiting factor for electric and magnetic interactions in space. When the ZPE strength was very small, atomic plasma and light processes were all very fast. So all plasma interactions were much faster in the beginning when the ZPE was minimal. As a result, the speed of plasma processes must be factored in with the zero-point energy curve. When that is done, we have a precise agreement with both the scientific data and the biblical timescale of a creation of our entire universe in 6 literal days. We have already seen how plasma processes can overcome some of the time issues with the standard model in astronomy. This is the first part of the answer. But plasma processes and their rate of interaction is controlled by ZPE strength. So in order to get the second part of the answer, we must apply the ZPE correction to plasma processes. When that is done, the complete answer to the time problem emerges. It solves all the scientific time problems as well as the biblical ones. We can account for the universe out there. But what about our solar system? We know that it basically obeys the laws of gravity. All the NASA spacecraft prove that. It is true that gravity does work on a small scale, such as in our solar system, but gravity does not adequately explain how things formed or work on a larger scale. If we're going to actually deal with science, we have to look at the data, and our universe is, again, 99% plasma. That cannot be ignored in favour of the tradition of the gravitational model. Here is a simple illustration. We know that gravitationally induced movement causes heat. Although you can't tell, if you drop a rock from the top of a 10-story building, it will be a tiny bit warmer when it hits the ground than when it started. Do you want gravity to warm your cup of coffee or tea? If so, you would be quite an age before your first cup was ready. We know to use electricity, electromagnetism, because it does the job so much more rapidly. That is how God did things too. When we put it all together, here's what we find. Using known plasma physics and the ZPE correction, it turns out that the Bible has known what it was talking about all along. First, space was stretched out just as God said. Second, the elements were formed very quickly out of the water plasma, Genesis 1, 1 and 2. Third, the centres of all the galaxies were formed and lit 12 hours after creation, creating the first dawn, Genesis 1, 5. Fourth, the stars in the galaxy arms, like our sun, lit about 4 days later, Genesis 1:14. Fifth, the Earth's early light was from our quasar in the middle of our Milky Way galaxy. The Sun took over on day 4. This is Genesis 1:2-4.
What we have done here is not invent something to try and support the Bible. Rather, we've taken the research of many scientists over many years in the areas of astronomy, geology, physics, and put it together and say, look where this leads. For millennia, people have trusted by faith in God and the Bible and had their experience of the Lord in this way. What we have in this day and age is something unique. We have scientific proof that the scriptures can be trusted and that the creation account is accurate, scientifically as well as spiritually. Thank you very much.